We are down now to the last 3 modules in basic calculus. In this video, we will stick our attention on how to approximate the area of a region under a curve using left, right, and midpoint Riemann sums. Also, we will discuss the introduction to the definite integral. Geometry, as we have known, provides formula for the area of region bounded by straight lines, like polygons. For a regularly shaped region, like the shaded region on the graph, using geometry alone to compute for the area is quite impossible. Finding the area of a circle is not an exception. Before, people tried to approximate the area of a circle by inscribing a sequence of regular polygons, each with double the number of sides than the previous one. In this diagram, a 4-sided polygon is inscribed by the first circle. For the second circle, an octagon or 8-sided polygon is inscribed, and a 16-sided polygon for the third. As the number of sides increases, the error of approximating the area gets smaller and smaller. This method is called the method of exhaustion, which is attributed to the ancient Greek mathematician Antiphon of Athens. For this diagram, we can approximate the area of the shaded region using rectangles. Thanks for the effort of the mathematician Georg Friedrich Bernhard Riemann. Until today, in his honor, we have the known Riemann sums. To illustrate Riemann sum, here are the following assumptions. The function f is positive. Its graph is located above the x-axis. F is continuous on the closed unbounded interval AB. The goal of this lesson is to approximate the area of the region R bounded by y equals f of x or the graph itself, x equals a or the left endpoint, x equals b using the right endpoint, and the x-axis. Considering the graph on the right, that region R is the shaded region. As mentioned earlier, we will use rectangles in approximating the area of R. To equally divide the region, we will identify first the partition points. Divide equally the closed interval AB into n subintervals. To do this, we compute the step size or the length of each subinterval. Suppose the closed interval is 2, 10. 2 as the left endpoint and 10 as the right endpoint. And from the interval, the value of A is 2 and the value of B is 10. Using the formula for n equals 2, the step size is positive 4. For n equals 4, the step size is positive 2. And for n equals 8, we have 1 for the step size. As n increases, the step size decreases. For n equals 4, there are 4 rectangles to be constructed. For n equals 8, there are 8. As to the value of n, in our lesson, it will be identified ahead for your reference. But take note, as the number of rectangles increases, the Riemann sum becomes approximately exact of the area of R. When we say Riemann sum of f, we refers to the number equal to the combined area of these rectangles. If you are asked to subdivide the closed interval 0, 1 using n equals 4, we need first to compute for the step size. Since b is equal to 1 and a equals 0, so the class size is 1 minus 0 over 4 or 1/4. After that, divide the interval 0, 1 into 4 equal parts, and each part has 1/4 step size. Based on this illustration, the first subdivision is from 0 to 1/4. The second subdivision is from 1/4 to 2/4 or 1/2. The third subdivision is from 1/2 or 2/4 to 3/4, and the last subdivision is from 3/4 to 1. So this is how to divide the closed interval using a certain value of n. There are 3 common notions for Riemann sum: the left, the right, and the midpoint Riemann sum. For the left Riemann sum, consider this illustration. The region is subdivided into 3 subintervals, so we have 3 rectangles. On the x-axis, we have x sub 0, x sub 1, x sub 2, and x sub 3 as the points. Recall that to solve the area of the rectangle, the formula is length times width. Observe now the first rectangle. Its width is x sub 1 minus x sub 0. For the second rectangle, that is x sub 2 minus x sub 1. And for the third rectangle, x sub 3 minus x sub 2. We will now identify the height of each rectangle. This height represents the dimension length. Since this is called the nth left Riemann sum, we will only consider the left endpoints of the height. Observe the first rectangle. The left endpoint is the encircled one, x sub 0. Since the function is y equals f of x, and for that left endpoint, the x coordinate is x sub 0. So, the height of the first rectangle, by substituting x by x sub 0, is f of x sub 0. For the second, f of x sub 1, and f of x sub 2 for the third. That measurement of height will be our length. Again, to compute the area of the rectangle, we will simply multiply the length and the width. By using the definition of the Riemann sum, that is the total area of the rectangle, so the third left Riemann sum, or the L sub 3, is equal to the sum of the area of the three rectangles. We will now substitute the area of every rectangle from the table, so we have that substitution. Since x sub 1 minus x sub 0, x sub 2 minus x sub 1, and x sub 3 minus x sub 2 represent the step size, so we substitute those variables by the symbol of the step size. By factoring out the common step size, so the equation now becomes f of x sub 0 plus f of x sub 1 plus f of x sub 2 times the step size. Take note that the step size is uniform to all rectangles present. For left Riemann sum, the general formula is L sub n equals the summation of f of x sub k minus 1 times the step size, where k is from 1 to n. For example, find the fourth left Riemann sum of f of x equals x squared on the closed interval 0, 1. This is the graph and the subdivisions of four rectangles. Take note that the x sub 0 is the origin, the x sub 1 is 1/4, x sub 2 is 1/2, x sub 3 is 3/4, and x sub 4 is positive 1. For the first rectangle, the left endpoint is 0, and for the fourth rectangle, the left endpoint is 3/4. Earlier, we get the value of the step size, which is 1/4. Now, we will compute for the fourth left Riemann sum, or the L sub 4. By using the general formula of the left Riemann sum, so this is now equal to the summation of f of x sub k minus 1 times the step size, where k is from 1 to 4. And we have the sum of f of x sub 0, f of x sub 1, f of x sub 2, and f of x sub 3 times the step size. And since x sub 0 is 0, so we have f of 0. X sub 1 is 1/4, so we have f of 1/4. X sub 2 is 1/2, so we have f of 1/2. And f of 3/4 for x sub 3. The step size is 1/4. So we will now evaluate the function f of x equals x squared using that four values of x. Because the function is x squared, we square the 0, 1/4, 1/2, and 3/4. And we multiply the step size, which is 1/4. So the L sub 4 is equal to 0.21875. For the right Riemann sum, observe now this illustration. Focus your attention to the right endpoints on the top of the rectangles. For the first rectangle, the width is x sub 1 minus x sub 0, and the height is f of x sub 1. Since the right endpoint of the first rectangle is x sub 1. For the second, the width is x sub 2 minus x sub 1, and the height is f of x sub 2. And for the third, the width is x sub 3 minus x sub 2, and the height is f of x sub 3. By that, we can solve the area of every rectangle by multiplying the length and the width. This time, we are going to solve for the third right Riemann sum. To solve for the third right Riemann sum, we will add all the areas of the three rectangles. So we have r sub 3 equals area of the first rectangle plus area of the second rectangle plus area of the third rectangle. The area of the first rectangle is f of x sub 1 times x sub 1 minus x sub 0. Copying also the area of the second and the third. And we will change the x sub 1 minus x sub 0 into the step size. So we have f of x sub 1 times the step size plus f of x sub 2 times the step size plus f of x sub 3 times the step size. And getting the common step size, so we have f of x sub 1 plus f of x sub 2 plus f of x sub 3, and multiply everything by the step size. Therefore, for the right Riemann sum, the general formula is in the form r sub n is equal to the summation of f of x sub k times the step size, where k is from 1 to n. Let's have now the example for the right Riemann sum. Find the fourth right Riemann sum of f of x equals x squared on the closed interval 0, 1. Observe the difference of this graph to the graph of fourth left Riemann sum. Since this is fourth right Riemann sum, the height of the rectangle depends on the right endpoint. Observe that all the rectangles are above the graph of f of x equals x squared, because the right endpoints are higher than the left endpoints. By using the formula of the right Riemann sum, we have f of x sub 1 plus f of x sub 2 plus f of x sub 3 plus f of x sub 4 times the step size. We substitute x sub 1 by 1/4, x sub 2 by 1/2, x sub 3 by 3/4, and x sub 4 by 1. And we already have the step size, which is 1/4. And since the formula is f of x equals x squared, so we square those number. So we have 1/4 squared plus 1/2 squared plus 3/4 squared plus 1 squared times 1/4. So that is now equal to 0.46875. So this is the approximate area of the region using the right Riemann sum. To understand the midpoint Riemann sum, let us refer to this graph. The height of the rectangle depends on the midpoint of the left and the right endpoints. In the first rectangle, the endpoints are x sub 0 and x sub 1, and its midpoint is denoted by m sub 1. M sub 2 and M sub 3 are the midpoints of x sub 1 and x sub 2, and x sub 2 and x sub 3 respectively. Therefore, the third midpoint Riemann sum is equal to f of m sub 1 plus f of m sub 2 plus f of m sub 3 times the step size. In general, to get the midpoint Riemann sum, we have the formula m sub n equals the summation of f of m sub k times the step size, where k is from 1 to n. Before you can use the general formula, take note that the m sub k is the midpoint of the two endpoints. Remember this midpoint formula, x sub 1 plus x sub 2 over 2. Just add the two endpoints and divide the result by 2, and that's your m sub k. For instance, find the midpoint of the following. The interval 0 to 1/4. To get the midpoint, just add 0 and 1/4 divided by 2, so we have 1/8. This 1/8 is your m sub 1. And the 7 over 8 as the midpoint of 3/4 and 1 is our m sub 4. For this example, we are going to compute the fourth midpoint Riemann sum of f of x equals x squared on the same interval 0, 1. Using the general formula, we have f of m sub 1 plus f of m sub 2 plus f of m sub 3 plus f of m sub 4 times the step size. M sub 1 is 1/8, m sub 2 is 3/8, m sub 3 is 5 over 8, and m sub 4 is 7 over 8. And the step size is 1/4. M sub 4 is equal to 0.328125. The three Riemann sums have different approximated value. Among them, which do you think has the closest value to the area of R? I just leave this question for you to think of. In your activity, you need to include the graph of your answer. How to graph? Just follow the steps. First, use graphing application to see the behavior of the function. This is the graph of our f of x equals x squared. Second, cut the graph within the given interval. Since the given interval is 0, 1, from that graph, we will just copy the graph within that interval from 0 to 1. Next, solve for the step size. In this given, the step size is 1/4. Divide the interval using the step size. From 0 to 1, we have that division using the step size 1/4. Draw the n numbers of rectangles. The value of n determines the number of rectangles. In this case, since this is fourth left Riemann sum, so the number of rectangles should be 4. And lastly, for the height of the rectangle, pay attention to the words left, right, or midpoint. We will now proceed to the relationship of the Riemann sum and the definite integral. We will now formally define a Riemann sum denoted by this notation as the sum of the series of n rectangles along the interval AB with bases of the same width, the step size, equal to b minus a over n, and with heights of f of x sub k determined by arbitrary values of the given function. It has been proven that the limit at infinity of the Riemann sums is the exact area bounded by the graph of f of x from a to b. Such limit has a specific identity and notation called the definite integral, which is denoted by this. The integral of f of x dx from a to b. A is the lower bounds and b is the upper bound. Take note that a and b are the limits of integration. With that, the formal definition of definite integral is as follows. Let f be a function defined on the closed interval ab. Then the definite integral of f from a to b, denoted as this notation, is given by the integral of f of x dx from a to b, and this is equal to the limit of the summation of f of x sub k times the step size, where k is from 1 to n as n approaches positive infinity. Take note, the greater the value of n, the closer it gets to the exact area of R, and this number n approaches to positive infinity. We will now proceed to the introduction of the fundamental theorem of calculus as well as the different theorems for the definite integral. Here is the definition of the FTC, or the fundamental theorem of calculus. Let f be a continuous function on the closed interval ab with antiderivative f. Then, the integral of f of x dx from a to b is equal to the big F of b minus the big F of a. Since a definite integral is the limit of Riemann sums, you have to put in mind that it would be difficult to compute definite integral exactly. However, the fundamental theorem of calculus provides an easier way of evaluating definite integrals on the condition that you can find an antiderivative big F of x and f of x by simply calculating the difference of big F of b minus big F of a. In cases wherein you cannot find an antiderivative of f of x, you must consider calculating the sum of the areas of the left, right, and midpoints of each rectangle to approximate the definite integral. The approximate is also an estimate of the difference big F of b minus big F of a. The definite integral is the area of the region bounded by y equals f of x, the x-axis, x equals a, and x equals b. This is quite familiar because these are the assumptions for Riemann sum. Take note that the definite integral is the limit of Riemann sums. Other representation of the definite integral using other variables look like this. Here are the different properties of the definite integral. Take note of some minor typographical error found on the module. For Theorem 17, the linearity of the definite integral, let f and g be positive continuous function on AB, and let c element of the real number. Then the integral of c f of x dx from a to b is equal to c times the integral of f of x dx from a to b. And the integral of f of x plus g of x dx from a to b is equal to the integral of f of x dx from a to b plus minus the integral of g of x dx from a to b. For the definition, let f be a continuous function on AB. If f of a exists, then the integral of f of x dx from a to a is 0. Take note here that the lower is the same as the upper bound. And the integral of f of x dx from a to b is equal to the negative of the integral of f of x dx from b to a. Here we interchange the lower and the upper bound. For the Theorem 18 or the additivity of the definite integral, if c is an element of the interval AB, meaning to say c is in between AB, so a is lower than c and b is greater than c. Then, the integral of f of x dx from a to b is equal to the sum of the integral of f of x dx from a to c and f of x dx from c to b. For the net signed area, just remember that the areas above the x-axis are positive and negative areas for the regions below the x-axis. Hence, if we suppose that f is continuous function on AB without considering whether or not f is positive, then the definite integral of f of x dx from a to b is the net signed area of the region with boundaries y equals f of x equals a, x equals b, and the x-axis. The net signed area equals the sum of all the areas above the x-axis minus the sum of all the areas below the x-axis.